Dear students, very good afternoon. Today we will be discussing 2D transformation and its role in computer graphics. As we know what is computer graphics, generating images with the help of computers. Computer graphics is a very powerful tool for rapid and economical generation of pictures. It has got lot many applications in every domain like engineering, architecture, medicine, entertainment, fine arts, commercial arts, etc. In all these fields, computer aided methods are routinely used in the design of buildings, automobiles, aircrafts, watercrafts, spacecraft, textiles and many other products. Now, the question arises how the image is described, how the image is generated. To generate any image, first we give the input, the description of the image, that is called the model of the product. That model is processed by the help of graphics algorithms and a synthetic image is created on the computer. So, to describe a picture, there are many ways. In raster scan applications, a picture can be described using the set of intensities for the pixel positions in the display. On the other extreme, if we are using a vector display, we can describe a picture as a set of basic geometric structures such as straight line segments, polygon, circle, ellipse, etc. And the basic operations that are performed on points and vectors, those are dot product and cross product. Once the picture is described, that pixel array is loaded into the frame buffer or the scan conversion is used to draw the basic geometric structures on the display. Now, if we have only the basic primitives, then we can create only very simple pictures. But in modeling applications, in design applications, we want to create many complex drawings and models. So, there comes the role of transformation. Transformation which translates, rotates or deforms the basic primitives, geometric structures to create the images of interest. So, that is the need of transformation. In order to generate a picture, we need not only to specify a model, but also manipulate the model in order to create more interesting images, because all graphics packages, they just support only algorithms for drawing the basic primitives. Other complex structures, they are drawn by manipulating these basic primitives with the help of transformations. So, this is the need of the transformation. In design applications, pictures are constructed from few basic shapes by scaling, positioning and rotating or by deforming the basic shapes. So, what is a transformation? Basically, it is a mathematical operation. That's mathematical operation changes object's position. Changing the object's position is called a translation of the object. It may change the orientation by rotating the object. We can change the size of the object by scaling or descaling it. Its ultimate result is the altering the coordinate description of the object. That means a transformation maps a point x y in one coordinate system to another point x dash y dash in another coordinate system. The new description of the point is written as a linear equation, linear transformation a x plus by plus c, and this means a new coordinate x is produced by changing by relating the value of previous coordinates x and y by some linear equation. Similarly, y dash is also generated by using some linear transformation. Now, how this transformation is presented mathematically or performed by the graphics tools. We see in mathematics, these linear equations can be represented by using matrices. So, before going into the details of the transformations, I would like to give some overview of the matrix operations also. So, what is the ultimate use of transformations? It positions the objects in the scene, it changes the shape of the objects, we can create multiple copies of the objects, or we can create the projection for virtual cameras, and animations are not feasible without transformations, and all video games or computer games or computer movies, they require animation. What is animation? It is the moving artificial movement of the object. In animation, a object is repositioned and by changing its orientation and position. So, without transformations, we are not able to generate any computer design, any computer games or movies. So, they are very, very useful. The basic transformations are translation, rotation and scaling. As the name suggests, translation repositions the object, rotation rotates the object by some angle, either along the x axis or along any arbitrary axis or along y axis, and this is the isotropic scaling. We are scaling the object by uniform value both in the x direction and y direction, so that the shape of the object remains preserved. Other transformations, those are called the deformable transformation, because they do not preserve the original shape of the object. These are shearing, tapering, twisting, reflection. All these transformations can be achieved through the basic transformations. Also, further, these transformations can be combined, and all these transformations are invertible. For a given transformation, we can write the inverse transformation also, so as to retrieve the object to the previous location or a previous angle. So, basic transformations are the rigid body transformation, which preserve distances and angles. These transformations include translation, rotation and identity. Other transformations are non-rigid transformation or deformable transformations like shearing and scaling. They deform the change the shape of the body. In translation, just object is displaced. There is no change in the shape, all the angles are preserved, all the distance between the eyes and face, all these things are preserved. So, the translation is a rigid body transformation. In rotation also, angle and distance between the basic points comprising the object, that is preserved. So, rotation is also a rigid body transformation, but in scaling, as we can see, the distance between the eyes is reduced and distance between the eye and the lips is also reduced. So, this is a deformable transformation or non-rigid transformation. Similarly, in shear also, it also changes the shape of the body. So, transformations can be broadly classified into two types, rigid and non-rigid transformations. Non-rigid transformations are used in complex design application. Basically, we use rigid transformations. As I have already told, transformations are represented by linear equations, and matrix is a very powerful way to represent these transformations. So, before going into the details of the transformations, we need to understand some fundamentals of matrices. So, let me give a quick review of the matrices. What is a matrix? A matrix is nothing, it is a rectangular array of numbers. A is the name of the matrix, and these numbers represent the elements of the matrix. These are number of elements in a row and column determine the size of the matrix. This is a 3 by 3 matrix. This means there are 3 rows and 3 columns. The first element in the first row and the first column is denoted by A11. This means this is the element on the first row and first column, and generalized notation that is used for representing an element position is Aij, where I is the row index and j is the column index. In mathematics, we start indexing at 1. This means 1, 2, 3, 3 rows and 3 columns, whereas in C language indices start from 0. So, generally first row is represented by index 0, second row index 1 and third row by index 2. Once we know how to write a matrix, so there are basic operations which can be performed on the matrices like on the scalars. Like we can add two scalar, addition is equivalent to scalar addition. Given two matrices A and B, if we want to add B to A, then we need to add the individual elements of each row and column to the other corresponding elements of another matrix, and the resultant matrix contain the sum of these two elements. But for addition to take place, this means size of the matrix should be same. If the first matrix of the size 1 by 3 and other matrix is size 2 by 2, we cannot perform the addition. So, the constraint on matrix addition is two size of the two matrices should be same. Let us take the example. These are 2 by 2 matrices, one containing elements 1, 2, 3, 4, 5, 6, 7, 8. So, after the addition result will be 1 plus 5, 6, 2 plus 6, 8, 3 plus 7, 10 and 4 plus 8 is equal to 12. So, matrix addition is very simple. Another very important operation which is frequently used in transformation, that is multiplication. All transformation require matrix multiplications. So, if we want to multiply two matrices A and B, that is B by A, then their size, there is a constraint that if A is of size n by m, then B must be of m by p. This means number of columns in the first matrix should be equal to the number of rows in the second matrix. Otherwise, you cannot perform the multiplication. This constraint is imposed due to the method multiplication is performed. To multiply two matrices, we multiply the I kth element with k jth element, then we perform the summation over the whole row where whole column. Basically, we multiply the first row of A with the first column of B and put this element in the C11 element of C. Let us take example so that you can understand. So, if it's a 3 by 3 matrix and this is 3 by 2. So, it satisfies the condition that number of columns in this first matrix are equal to the number of rows in the second matrix. So, we can multiply these two matrices. How we perform the multiplication? We multiply the elements of the first row with the corresponding elements of the first column. This means 2 multiplied by 6 plus 6 multiplied by 3 plus 7 multiplied by 2 and result is 44. This we place at first row first column. Now, first row second column, so second element will come out to be 2 into 8 plus 6 into 3 plus 7 into 676. Similarly, we multiply second row with the first column, we get this element. Multiply second column with the second row with the second column, we get this element. Then we consequently perform multiply third row with the first column, we get 3 1 element, and third row with the second column, we get this 3 2 element. So, resultant matrix size is number of rows in the first matrix and number of columns in the second matrix, that is 3 by 2. Here in this example, number of columns in the first matrix are not matching with the number of rows in the second matrix. So, we cannot multiply these two matrices. So, therefore, the mandatory condition for multiplication that these two matrices should satisfy the number of rows of the columns of the first matrix should be equal to the number of rows of the second matrix. After understanding multiplication, let us review some properties of the matrices. Unlike scalar multiplication, AB is not equal to, this means the order of multiplication matters. If we multiplied by B by A, it is not same as if we multiplied A by B. Matrix multiplication distributes over addition. This means A into B plus C is equal to individual multiplication then addition. Either we first sum the matrices then multiply, or we first multiply the individual matrices then sum over it. This is called distributive property, and these are the identity matrices of size 2 by 2 and 3 by 3. If we multiply any matrix by identity matrix, the result remains the same. Now, once we have knowledge of the matrices, now let us see how the transformed equations are represented by using the matrices. As I told you, a transformation maps the point x by to a point x dash by using this equation. So, this equation can be written in the matrix form. These two equations can be written in the matrix form: x dash y dash, a column vector, is equal to a, b, d, e and these variables x and y plus constant c, f. So, this is a transformation matrix which will define the type of transformation that is to be performed on the original point x, y. The values of this transformation matrix will decide how the point is going to be transformed in the new point. This Cf is a constant vector. This may be 0 or it may be having some value depending upon the transformation. So, any transformation can be represented using either a multiplication operation or a additive operation. So, both operations, multiplication as well as addition operations, are required to accomplish the transformation in graphic systems. Now, let us go to the basic transformations. The three basic transformations are translation, rotation and scaling. So, what is translation? Translation positions the object in the scene. It is a very basic transformation and very easy to accomplish. It is example of rigid transformation. It does not deform the shape of the object, simply repositions the object. A translation is applied to an object by repositioning it along a straight line path from one coordinate location to another. A 2D point xy is translated by adding translation distances to the original coordinate position so as to move it to the new coordinate position x dash y dash. We are not changing the shape, simply we are displacing, we are changing the values of x and y. So, simple translation can be accomplished by a addition operation. For example, we want to translate point P to a new point P dash. So, how? Let us say x and y are the coordinates of the original point P and x dash y dash are the coordinates of the new point x dash y dash. So, to perform this translation, we need to know the distance between the x dash and x and y dash and y. So, if we add that translational distances to the individual coordinates, then we get the new point coordinates. P dash is equal to P plus T, where T is equal to a column vector Tx and Ty and P is a column vector containing the original coordinates x and y. This means a transformation can be accomplished by adding two matrices. First matrix contains the original coordinates of the point and T is the translational vector containing the translation distances both in the x direction and y direction. This x direction and y direction. So, let us take example. We want to transform the point having coordinates 10, 10 to 30, 25. This means translational distance in the horizontal direction, x direction is 20. So, Tx is equal to 20 and in the y direction it is 15. So, we can add, by adding these distances to 10, 10, we can translate the point P to P dash, where the coordinates of P dash are 30, 25. Now this was all about the translation of a point, but ultimately a scene, there are the basic structure, basic primitives like line, polygon, circle, ellipse or other complex shapes. So we want to perform the same transformation on an object. So how to apply translation on an object? So for example, the object is a line segment, then to move a line segment, apply the transformation equation to each of the two line endpoints, because a line in graphics packages is defined by two endpoints. So if we know the endpoints of the line, we can draw the line with the help of line drawing algorithm. So how to perform the translation of a line? You apply the translation transformation to the two endpoints and redraw the line between the new endpoint. Similarly, to move a polygon, to reposition a polygon, apply the transformation equation to the coordinates of each vertex. For example, polygon contains 5 vertex, then we will have to apply this transformation to all the 5 points and then redraw the polygon using the new set of vertex coordinates. Similarly, a circle can be repositioned by applying the translation to the center of the circle. Similarly, to the ellipse and other complex shapes can be translated by applying the transformation to all the set of coordinates which will describe the shape of the object, and then redraw the object with the new set of points. So, object can be, this equation shows the repositioning of the object. This is any object containing 4 line segments and 1 triangle. So, this object can be described by how many points? 1, 2, 3, 4, 5. So, we will have to apply these transformation to all these 5 points and redraw the shape with the new points. So, mathematically in the matrix form, a translation can be represented as a addition operation. The first matrix contains the original coordinates and the second matrix contains the translation distances in various directions. This is an example of translation. The triangle having the coordinates, first vertex having the coordinate 1, 1, 3, 1, 2, 3, and we want to translate this triangle to the new coordinates. Here, if we know this vertex position where we want to reposition the triangle, this new vertex position is 6, 4. So, what the translation distance? Translation distance comes out to be 5 in x direction, that is Tx is equal to 5 and Ty is equal to 3. This vector 5 and 3 vector will be added to each vertex position. This means it will become 7 and 6, this will become 8 and 4. Now, using the 3 new vertices, a triangle can be drawn by applying the line drawing algorithm. So, in a scene or a picture, you can reposition any object. This repositioning transformation is very, very useful in animations where we want to show the object moving. So, to show the movement, what we need to do, we have to draw a object at one position and after some time we will have to erase the previous object and redraw the object at another position if we do not want to change the shape. So, simple movement of a ball or a car can be shown with the help of translation transformation. It is very simple to implement because addition is a very, very efficient operation. So, 2 matrices can be added with the simple number, these require number of operation equal to the number of elements in the matrix. So, what are the properties of the translation transformation? If the translation distances are 0, 0, the transformation is identity, means object will remain at the original position. 2 successive translations are additive, means first we displace the object, then again subsequently we displace the object by another distance, then the same 2 transformations can be achieved by adding the translation distances. And so, for every transformation there exists a inverse transformation in which the simply translation vector will be replaced by the negative values of the translation distances. Now, let us move to the new transformation, second scaling, which is very useful too, because in most of the scenes we want to show the rescale the change the size of the object. For example, we draw a small circle in another position, we want to show कि circle has been enlarged or has been become smaller. For example, we want to throw a ball at a distance from the ground, we want to show it with a small ball. When it will come again back to the ground, we want to show with the same size. So, scaling is required to perform this type of transformations. As the name suggests, scaling transformation, it alters the size of the object. It can in scaling we can specify how much bigger or smaller we want to make the object by defining a scale factor. This scale factor is a positive value. If the this scale factor is greater than 1, this means we are enlarging the object. If this is less than 1, this means we are reducing the size of the object. For example, if the scale factor is 2, this means we double the size of the object. If we reduce it to half, that is less than 1, then we will reduce the size of the object by half. Now, how to perform this transformation? Let us say we want to scale point p x pi by some scaling factor x x and x s y. These scaling factors are the represent the values that we want to give in the x and y direction. Generally, s x is taken equal to s y if we want to apply the same scaling in both the direction, in all the direction, otherwise it will change the shape of the object. To scale it to a new point p dash, what we do, we simply multiplied the value by the scaling factor, x coordinate by s x and y coordinate by s y, and we get the new points x dash, y dash. Y dash is equal to s y into y and x dash is equal to s x into x. As we can see, this x dash value is less than x and y dash value is less than y. This means scaling factors are here less than 1. This scaling reposition is changing the position of the, let us see, observe it. Scaling not only changing the size of the point, but it also repositioning the point, means negative. How it happens, why it happens? We will see in the subsequent slides. Let us first take some facts about the scaling. Any positive numerical value can be assigned to the scaling factors s x and s y. Values less than 1 reduces the size of the object and greater than 1 produces enlargement. Specifying 1 for both s x and x y leaves the size of the object unchanged. When s x and s y are assigned the same value, this means a uniform scaling is performed in all the directions and that maintains a relative object proportion, means circle will remain circle. But if we don't assign same values to s x and s y, a circle will become ellipse. These unequal values result in the differential scaling. There are two types of scaling, uniform and differential scaling, and this differential scaling is useful in design application, like where we want to show morphing and other things. So, any object can be scaled simply by multiplying the individual coordinates of the object by the scaling factors. These scaling factors will represent the transformation equation. So, if the original coordinate is 2 1 and scaling factor is 3, so the new coordinate will become 6 and 3, and this is 3 1, the new coordinate will become 9. Similarly, this point will be changed to some, and you redraw the object. Now, the result is the scaled object, which is 3 times bigger than the original object, but we wanted to perform only scaling, but this object is repositioned. This repositioning is the result of that we are performing scaling with respect to origin. If we perform scaling with respect to some fixed point, then repositioning will not take place. But scaling with respect to some fixed point, that will be a result in a composite transformation that we will understand after understanding the basic transformations. So, objects can be